All right, great to see everyone. This is one of the largest stage I've ever been on, so fantastic. So let me start from a first warm-up question. How many of you know what quantum computing is? Okay, quite many. That's cool. That's great. I was a bit afraid that there are like that installation in the front, like AI, and I was thinking like everyone is only about AI here, but that's still not bad. AI actually drives hype for quantum computing, so it's also a good thing. And with that, let me start. Oops. It doesn't click. Okay. With that, let me start. AI hype actually drives the compute hunger. Now compute is a new kind of gold. We all want larger data centers. We want more GPUs for our LLM training. And we want this to be accessible right on demand today. And for example, in Texas, we see those massive projects being built, like 500 billion Stargate project to build a huge data center to host a lot of AI capabilities of US companies like XAI or OpenAI. But there will never be enough of those on the planet Earth. And now there is this interesting trend of another wave of space exploration where we see data centers being built on the orbit of the Earth. And just a few weeks back, I met with a person from the company called Star Cloud, and they just ran the first LLM training on the orbit of the Earth. But what's more interesting that there are challenges in the world, challenges of the humanity, when there will be never enough compute on the planet, on the orbit, even if you build the Stargate-like clusters on every continent, and even if you will put all the orbit will be covered with data centers in the space, you will still not have enough compute to compute those challenges. And some of them are those which we actually feel almost every day. For example, like if you want to have a personalized drug, we need, in order to build it, we need actually to simulate on the very low level how this drug actually interacts with our cells. We can't model all of those interactions today with the present computer. Even we cannot model the weather good enough to be sure when thunderstorm will happen in different parts of the planet, or model other like natural phenomena. And that's a huge challenge for logistics or supply chain. And particularly in the logistics and supply chain, it's also a large optimization problem with many degrees of freedom, which is very hard to model today on these present state computers. In order to do so, we need a different kind of compute, which will be able to do that. And so far, none of existing infrastructure allow you to do that. But somehow, nature does that instantly and very easily on the large scale, billion times per second. We see it in every interaction in our cells, in every cloud, in every bird which flies in the air. We see those simulations being happening instantly, and somehow nature does those easily without need of that gigantic compute. And today we have these new machines called quantum computers, which can harness this power of nature and allow us to do these kind of simulations. And these machines are already here today, and they have some kind of superpower in comparison to classical computers. My name is Mykola Maksymenko. I'm co-founder of Haiqu. We build software which allows us to give superpowers to these present quantum computers today. And before we go into how this all works, let me outline where we are today. So quantum computers are already here, and they already promising interesting results all over the space in different industries, for risk analysis in finance, for simulating small molecules for drug discovery, for logistics optimization, and many other domains. Like overall value that we predict will happen at around 2040s will be measured in hundreds of billions. It will be much bigger thing than what we see in AI today. But in order to get there, we still need to get through some stages. So what's so different with quantum computing in regards to classical computing? So first of all, we can look at what are actually those building blocks of quantum computing. And the major building block is the qubit itself. It's a quantum bit. If you look on classical computing, we operate with binary numbers, zeros or ones. You can see it as arrow which looks up or down. And that's all. This is all it can express with a single bit. With a single qubit, you can go much into a larger expressibility. You can model all the numbers in between 0 and 1, and essentially this can be mathematically described as a vector on a sphere which can look whatever direction it wants. And this is much higher expressibility just with a single qubit. But imagine you have many of those qubits. And already for many qubits, for a single state, you can describe exponentially large number of information in a single state. That number is already larger than the number of atoms in the universe for a few hundreds of qubits. That's why it's impossible to do any simulations of the quantum systems on the scale of current classical data centers. That's why you need a different kind of compute, and that's why we need quantum computers. And already with 50 qubits, you can get beyond what's possible to do classically. You can simulate physical systems or chemical systems, which are just impossible to do on the classical computer. With 100 plus qubits, that's where already interesting applications in science, chemistry, physics lie, or some biology applications. And already today, we see some interesting research happening in this area. For thousands and plus qubits, there will be many interesting industrial applications which would drive next progress in the compute across many different domains. For some of the problems, we even don't know that they exist because they are so hard that we even don't look there. But believe me, they are there. And current modern quantum computers, they already have several hundreds of qubits. And it seems like, oh, wow, that's great. We can already model something bigger than possible model classically. But the problem is that all this picture is for ideal case, when you have so-called logical qubits or error-corrected qubits, but those which don't have any errors. In practice, things are much more messy. In practice, it looks like this. You have errors all over. Your algorithm is completely destroyed. And if you want to measure some reasonable result, you have complete random noise, which does not even have any signal about your original problem. And that happens because these quantum computers are still very fragile systems. They need to operate either at very, very low temperatures or at very low energies such that they can actually exhibit quantum effects. And that's very hard to achieve. It's actually an engineering nightmare to do in hardware. But nevertheless, we already have those machines which can do something interesting. So different kinds of noise, even cosmic rays, actually can destroy your calculations. And in order to think about that in comparison, you can already think that we are basically transferred back into the past, into the era of early classical computers, where computers operated with vacuum tubes, and those vacuum tubes could overheat. Those vacuum tubes can just break. And that was a nightmare actually for those engineers and early computer scientists to operate with those computers. And at that time, in 40s or 50s, there was no error correction. Error correction appeared on the horizon only at around 60s and started to be implemented in these machines. So these machines were very fragile, very incapable to do something big, but nevertheless, people used them for many interesting and useful applications at that time. Another interesting similarity with that age is that today, similarly to early days of computers, we still haven't decided what kind of building element to use. So there are so many different ideas and prototypes of qubits. There are photonic qubits, trapped ion qubits, superconducting qubits. As a non-expert, you probably get completely confused, like, what does it all mean? Like, is there a difference? And apparently there is. There are some pros and cons of using different types of qubits. For example, trapped ion qubits, they are more high fidelity, they have longer lifetime, but they are very slow in terms of computations. You have superconducting qubits. Those actually are high frequency ones. You can actually sample a lot of information fast from them, but they are much more noisy. They're actually much more fragile in terms of like all the different types of noise that I just described. There are Majorana qubits, which were just presented by Microsoft recently, and those qubits are protected by physical topological effects from noise, but currently we have basically only a prototype of a small number of those. It's very hard to scale. So with that, we are very much similar to where we were in the early stage of computing, and let me remind that that's not a bad thing. Already at that time, it took us around 26 to 30 years to converge on a single architecture which was scalable for the transistors which we have today in our computers. So we are still not there in quantum, but we can still already now do some useful things. And this diagram basically shows where we are today and where we can be projected. So with the current computers, we are on the level of few hundreds qubits. So that's achievable coherent state of these machines. And in order to get to fault-tolerant, error-corrected machines, we will need few thousands or tens of thousands qubits. And if we project what we have right now, so basically we started to get first processors at around 2014 and a bit earlier. And if you just like linearly try to project it, we see that that will happen like in around 15 years from now. So that's more or less what people typically say about quantum computers, that's like a decade or even more away from us today. But the question is that already now we hear about quantum advantage, quantum supremacy, and many big words and a lot of hype around quantum computers. And that's related to the fact that already today, you can run on this early stage quantum devices calculations which are impossible to reproduce on the classical computers. And that's called quantum supremacy. And the question is, can we use this capability of a quantum supremacy to run something useful? And here, the challenge is also apparently in algorithmic design, in software which we built for quantum computers. Apparently there are just like a handful of algorithms which are not of a classical nature and which harness the quantum effects of these devices and can lead us to some advantage. So building a quantum algorithm is not just taking your favorite classical algorithm and running it on a new device. This is a different type of a calculation. These are not just faster computers. This is not a GPU or a new type of phone or processor. This is entirely different paradigm in the way we build algorithms. So that requires you to design those quantum algorithms. So that requires some intuition and knowledge about quantum information. But also what's important, you need to have access to the device, to some of these larger processors in order to run, validate, see how it works in practice on the noisy device, and iterate before you actually get something useful and reasonable. And one great step, I would say humanity's small step, but it's a great step for the future of quantum computing, is that we now have a bunch of these large-scale devices available for everyone. So every one of you can actually register on, for example, AWS or IBM Quantum and access some of the largest quantum computers we have today. And try to run your own algorithms, try to run your own experiments and get results, iterate, and maybe you will find something useful. So IBM was pioneering that a few years back, where they offered larger scale quantum computers at that time of around 100 27 qubits called Eagle processor, available for everyone. So today there is a whole line of different machines of that scale between 127 and 156 qubits. You can access them almost instantly. You can set your algorithm in the queue, wait for a little bit and get it executed. There is IQM, European quantum startup, which also put their machines on the cloud through their own quantum cloud. There is Google, who instead of giving the public access, works individually with several academic groups. And that's already a huge progress, because with this access to these devices, we started to see that already today we can do something useful. That sparked the whole range of research across different disciplines, not only like quantum physics and quantum algorithm, but also like material design, chemistry, biology, optimization, and many other cases. So already on this list, there are just like a bunch of interesting use cases. It consists, for example, the first experiment by IBM. It consists like folding of mRNA molecules. It consists of optimizing some hard logistics optimization problems. And already today, you can run those on actual real devices at a large scale. And sometimes, what's most important, some of these results are easier to get on the quantum computer than running the same simulation on the classical. For example, if you want to fold a mRNA molecule, it will take you around 12 to 14 hours to run the same simulation on a classical computer, while you will get the optimal result already within the 40 minutes on the quantum computer. If you want to simulate some of the recent quantum echo experiment promoted by Google, it will take you many hours, maybe hundreds of hours of a classical compute to simulate, while you already can get the same result in a matter of minutes on the quantum computer. So these machines are already here, and we see their application in very niche cases here and there, such that we can start extracting value from them and scale it broadly. But in order to do so, all of us need to jump in and start experimenting with them. And that's apparently not that easy. So to run large-scale experiments, on one hand, as I said, you need algorithms. So you need to develop some algorithm or take existing one and apply it to your problem. But second big obstacle is actually not cheap. For example, this first experiment by IBM, where they applied quantum computing to a material design problem and simulated dynamics of electron function in the material, that took them nearly 10 hours to execute on the quantum computer for the successful case. While you can imagine that there were a lot of unsuccessful experiments, and it's already even successful case will cost you $30,000 to $50,000 to run this. That's ridiculously expensive for individuals, for researchers in academia, even for industrial R&D team, running something like basically producing one curve and paying $50,000, that's quite expensive. And moreover, in order to run this experiment and not produce garbage, you need not only like building the algorithm and mapping your problem into quantum algorithm, you actually also need to understand like how to execute something on the hardware. You need to understand about noise mitigation, synthesis of your algorithm into smaller compiled version, error correction, calibration, and many other things which altogether start building so-called middleware stack. So in classical software, we are very familiar about middleware, like compiler, that's basically a middleware. So now we are building something similar in quantum case. And that middleware apparently becomes a very big chunk of a work of a researcher if you want to run something useful. In classical case, it was not that much different. When the first computers appeared, first personal computers, they were like this. They were programmed on assembly. They were not very powerful. People even called them completely useless because they were actually had so little memory and processing power that you seemingly cannot run anything useful. Until actually these two guys jumped in and developed BASIC language. And this language opened up the first personal computers for much broader community, those who were having troubles programming assembly. Now with BASIC, you can actually start building algorithms which would be much more of a practical use, for example, some spreadsheets, some text editor or whatever, which suddenly build all this infrastructure and suddenly build all those applications that we have today in our computing. The more recent example are the graphical processing units or GPUs. We now associate GPUs with all this AI revolution, AI. But at that moment when CUDA was developed, these were very niche devices. They were like specifically for graphical processing and for some gaming developers. Now you can apply the same processing units for deep scientific simulations, for all the matrices processing in AI and training of large language model. And all that is because of the middleware stack, CUDA, which enabled that. And we need to build something like that now for quantum. At Haiqu, we basically do what Microsoft did for personal computing or CUDA did for GPUs. We do the same for quantum computers. We build infrastructure software which allows you to run much more on existing hardware at a much lower cost. We allow to run hundreds times more operations and at orders of magnitude higher speed and lower costs. In practice, it also allows you to run agnostically across different devices, not only IBM, but also IonQ, IQM, Rigetti, or other types of the devices which are available on the market. And altogether, this gives tremendous value. So if you would start earlier with the experiments which cost $30,000 per run, so now you can, with all this infrastructure, you can actually decrease the cost just below $100. With that, this kind of research is now available to every student, to every personal research project, and to many other people who just are newbies to quantum. Instead of running toy experiments on simulators, on few qubits, and like play what entanglement is, you can immediately try to do something useful at so-called utility scale of hundreds of qubits on real quantum computers. And this is, let me say, why, so what? So why do we need that if these devices are still very early? That's very important because that now allows you to experiment faster, iterate faster, and get towards use cases which potentially could bring value in the future or nearest future. And moreover, with this infrastructure, you can now run immediately on these machines at the largest possible scale. And just a few examples, with Airbus and Quantient, our partners, we run largest scale today of a computational fluid dynamics for wing design. With Capgemini and GSK, we run full simulation of a small molecule electronic dynamics, which was just impossible to do otherwise. With HSBC, we're first in the world and on the largest scale loading the real financial distributions into the quantum memory of the device, such that we can start processing this on the quantum device, such that they can start using these financial distributions for modeling, for example, of risks or derivatives pricing. And there are many other cases which are now in our pipeline, which we are building largest scale and most practical applications already today. And this opens up the roadmap and gives us hints where the quantum advantage will happen soon. Because currently these are prototypes. These are early trials, early adoption versions of algorithms. But sooner we will start building intuition and we'll start understanding where the quantum advantage can be in that or that business, and we'll apply the whole machinery of integration this into production. And one of such recent use cases, which was just like a few weeks old, is our new algorithm, which allows us to load practical scale data into quantum computers. So now you can load very large, high-dimensional data vectors into quantum computers. You can then process those feature vectors, and then you can use them in various AI applications. So, and that's basically a combination of quantum and AI. I still say this word here. And now you can think like where it's necessary, because current AI systems are already very powerful. Why do we need quantum here? And apparently there are problems which are still very challenging for classical AI. Those problems where the data is almost of a random nature, and it's very hard to classify and distinguish between different classes of that data. And one of such problems is anomaly detection. For example, if you have very high dimensional data for detecting anomalies in finance or biological systems. And for this kind of data, we consistently see that first processing this data on a quantum computer can actually give you advantage and improvement in solving the particular problem. And that's one of the first examples in the world of actually practical, useful quantum computing applied to an actual real-world problem today. And that was actually very much appreciated by financial guys. So they even covered us in American Banker Journal recently. While the problem was actually not applied to finance, but they were super excited about that. So now, let me give you a little bit of a perspective. So we started with, just a few years ago, we started with very small prototypes. When we started company, basically 3 years ago, the people were running some small things on the scale of 2, 5, maybe 10 qubits. And that was basically a toy examples which you can simulate on your phone, nothing special. Today, we can run larger scale simulations on hundreds of qubits, and many of them are nearly impossible to reproduce classically, even on the large clusters. So these are record-breaking applications. And we believe that with our technology, in the next few years, we'll be able to bring useful quantum computing few years ahead of everyone's expectations, such that we will be able to run useful applications in real-world big challenges. And when that will happen, everyone will start to care. And we see the repeating pattern. When hardware is being developed, initially, that kind of attracts a lot of value, a lot of interest, but then that's a software and applications which actually winning the market. And quantum will be no difference. With BASIC, with CUDA, with PyTorch, we were able to commercialize and bring big some of the world-changing platforms. And we expect that that will soon happen in quantum computing. So with that, you can be one of the first early adopters of this technology. Feel free to scan the QR code. And here I thank you.